Okay. Okay. So, and this is done in cooperation with a lot of colleagues, with postdocs, as Dennis and Martin, Kilian and Katharina, and the other ones are doctoral students. And you will see the faces 2 times later related to the different topics. The title is Porous Media Flow Coupling Model Concepts. And I will show you at the end how tricky it is. Okay, that's the only word I can show you. Let me start. You know this. I think we can couple the porous media with the free flow. On one hand, that we have on the top or the bottom free flow, and the rest is the porous media. Okay. There are different kind of application available. The first one is related to the interaction between the atmosphere and the water cycle, the unsaturated zone. The second one can be related to complex multi-component processes. You have a lot of components in the subsurface like CO2, methane, and so on. And if we have now this climate change processes, then we get an uncontrolled migration of these components into the atmosphere. And that's related to the increase of solar radiation and of increase of wind and temperature. And you cannot handle this with the Fickian law. Why? Very simple. You have a multi-component system. You need Maxwell-Stefan equation and so on. It's a really tricky thing to handle this. And of course, that's related to my question where I got an excellent answer from him yesterday, that it's not only temperature-driven and pressure-driven, that is density-driven and viscosity-driven too. Why? With this change of the components, you have a strong influence on density and viscosity. Okay, that was Katharina's PhD. She has developed the model and the concept with colleagues from Boulder together, where we have analyzed this a little bit more in detail. And that was one of the discussions that we have had yesterday too. That was what Danny has done. You will see we have published different kind of papers with Danny together, where we have analyzed with our model really evaporation and the influence of evaporation on one to the other one related to the interface. Okay. The next one is related to salt precipitation. We have discussed this kind of topics this morning. Salt precipitation is one of the key environmental problems worldwide. I will give you an example. We have a cooperation with the Technical University of Tunis. Tunisia, 25, in this case, 28% of the whole agriculture area is now blocked with salt. And this is related to, again, climate change. Why? You get higher temperatures, then you get an increase of evaporation, evapotranspiration processes on one hand. And of course, they use more and more fertilizers where you have salt involved. And of course, they need more water. And if they need more water, they drill deeper wells. And if you have deeper wells, then you have more salt in the system. It's really crazy, crazy circle. And here the key problem is, on one hand, to identify the onset time. Onset time in this case means, is it more density-driven instability that you get mixing, or is it more starting with the salt precipitation process, how they interact with each other? And then it's strongly dependent on the salt that you have in mind. If you have NaCl, then it's relatively light in comparison to gypsum. And it can be that you get a crust on the top of this porous media, or it can be that you get a crust inside the porous media related to the different processes, resistances, and so on. Really tricky. That's the first area of interest related to coupling free flow porous media flow. The second one is related to if the free flow is included in the porous media. Okay, one area is fractured media. For instance, if you have now open fractures, like where I come from, Michael knows this very well, there are castic systems. And castic systems, they have really holes in the system. These are really open fractures. And the question is really, how do you interact between the flow regime inside the fracture in the surrounding matrix? That is really, you must couple the free flow with the porous media. The second area is related to biomechanics. And it's done by Timo. He's now working with Simula in Oslo. That was a project with colleagues from Bern and Zurich together about multiple sclerosis in the brain. You have the vascular system on one hand, you see it here with the blue and the red part. And this is the capillaries, the very tiny ones, and this is embedded in the tissue, in the brain tissue, the gray and the white matter. And what kind of exchange processes do you have? How you can handle this? It's really tricky. If you are interested on this, we can discuss it later on. Okay, that's another example. Then that's a brand new project that's related to leaves. Why we are interested on leaves? Question to you. And normally I offer beer if I get a good answer. I can offer you water. Yes, that was a project. That was an idea from colleagues from the ETH Zurich. We have a lot of heat waves in cities, and this is a problem in Stuttgart and other towns now too, related to climate change. And one of the ideas is now to use more trees in the city. Why more trees? Very simple. You know this from your own skin. If you have more trees in a city, then you get a stronger evaporation process. If you have a high evaporation process, then you get this evaporation cooling effect. That's the first one. The second one, you get more shadow areas in the city. And the combination of both of them, I got it from colleagues from MIT, they taught us to get then a reduction of 4 to 5 degrees in cities. And it's very important, not only in Mexico, that's important now in the south of Germany and Italy and so on too. And the leaf is a very complex porous-medium structure. On one hand, you have the vasculars here, you see it here, we use this kind of model. And then of course, if you are interested on the tissue, then we used our porous-medium or pore-network model to combine this and to analyze this. And one of the stories that's here related to this experts here is the negative pressure. That means, for instance, how can the tree transport the water to the leaf, how they interact with each other, how we can optimize this in the sense of heat waves. Very, very nice project. Okay, and last but not least, fuel cells. I think fuel cells are really systems where you couple on one hand the free flow, that's the gas distributor, that's this one here, where you inject on one hand oxygen, on the other one hydrogen, then you get the electrochemical process at the reactive layer, and then you produce water, and you need good water management for this. Okay, and I have a share for hydromechanics. That's the reason why we are prepared for this. We have done a lot of work related to this with Bosch together. Bosch has now built in Stuttgart a research center, campus, with 400 people. Only these people work on fuel cells. And we got money from them. And this is related to the fuel cell. There's a big difference to the other ones. In this case, the diffusive layer is a hydrophobic material. So that with other words, the water is in non-wetting phase. And that means, for instance, you need now a trick to get out the water. That means to get the bubbles on the top. And of course, you need then a good concept that shares the bubbles into the free flow so that you get enough space again for the oxidant to transfer to the reactive layer with the hydrogen. Okay, if you are interested on this, that was a talk that I have presented last year in Bergen where we were together. Okay, if you're interested, let me know. You see, hey, a lot of things that we can do related to coupling free flow porous-medium. If you like it, I can show you more examples. Okay, so now you are highly motivated, and in the next 10 minutes, you are completely frustrated. Let me say it like this. At first, I will give you a short overview of the different processes. And that's related to what you have shown yesterday too. That's on a pore scale here. On one hand, of course, we have advection, diffusion, convection, conduction. No question. Then, of course, we have gravity forces, buoyancy forces, capillary forces, and so on. This is one story. The next story is that we have different kinds of interfaces of different levels. We have on one hand interfaces between the different fluid phases and the solid. You are the expert about this. And then we have different layers in the system. Layers means if we have now the free flow on the top, then if we're in a laminar regime, then we have the boundary layer. If we're in a turbulent regime, and normally we are immediately in the turbulent regime, then of course we have two layers in the game. The viscous sublayer, it's tiny, I will come back to this later on, and the turbulent boundary layer. And I will tell you later on why this is so important, especially related to diffusion and conduction. Okay, So the idea is now how we get the different interfaces layers as good as possible into our REV-based concepts. That is the main challenge. Okay, problem. Okay, let me summarize the interfaces before we come to the models. That means we have fluid-fluid interfaces. We must transfer this. Then we have layers in the system. We must integrate this. Of course, we have heterogeneities on the pore. We must integrate this in the REV-scale, so that we can really prepare a model that allows us to make really application-related calculations. Okay? Try to be clear. But we are far away from applications. But so, and of course, that is the story everywhere. That was you have presented very well yesterday. Sorry, that was my idea to get help from him with his talk. We must bridge the gap from the molecular, I call this now, to the application scale, REV-scale. And of course, if you be on a molecular scale, then you can think about absorption processes. We can think about the detailed processes at the interface and the interactions. We can think about heat transfer, mass transfer, and so on. Then, of course, we must transfer this in general to a continuum-based pore-scale concept, where we have sharp interfaces, very clear related interfaces, but this is not really what we can use for real applications. So that we averaged over this, and in general, we used any different kind of homogenization strategies, and in general, we get volume-based quantities. And if we have volume-based quantities, then we lost all this kind of information, interface-driven processes. We smeared out all this kind of effects. The question is how we can integrate this. Is it necessary? And this is then related to the REV-scale. Okay. So that means we need interface conditions for the fluid properties, interface conditions for objective parameters, and then of course we can handle this kind of thing. Okay. The idea is now for the next 30 minutes, understanding complex processes, momentum, mass momentum, energy on different scales, scale bridging, modeling concepts. Is it possible? And under which conditions? And now I will start the other way around to show you how much mistakes can a German professor do. Okay? I did it with Klaus Mostert. He's now assistant professor in Denmark, in DTU. And Klaus, I told Klaus, no problem. Klaus is an environmental engineer by training. I told Klaus, don't worry, I will write down the equation. You can integrate this in our model, and then it's finished after 2 months. It took us 10 years. Okay, I will tell you what. This is Klaus. Three of them are environmental engineers from Stuttgart. Katharina, she is now working for BMW for fuel cells, and he's working for Mercedes. And Klaus is a professor in Denmark. Okay, we have started with this free flow, porous media flow, and the porous media one is a multi-phase. I will show you this REV-based model that we use. Okay, that means we must have a clear understanding what's going in the free flow, what's going in the porous media, and at the interface. Okay, so you can use two different kinds of concepts. You can use the one domain concept, that's the Brinkmann equation. It's very well known for single phase systems, but we are interested on multi-phase systems. That's the reason why we use the second concept, the two domain concept. That means we have the one compartment that describes the free flow. Then we have a compartment that describes the REV. And then, of course, we have developed different kinds of interface conditions that takes care of the transfer, mass, momentum, energy between these two compartments. Yeah, it's clear for all of you? Super. So that's the model concept that we use. I will show you later on other ones. That means for the porous media, we have a multi-phase, multi-component non-isothermal concept, local equilibrium, thermal equilibrium. And in the free flow, we have one phase, the gaseous phase. And of course, we can describe advection, convection, conduction, diffusion, evaporation, condensation, degassing, and so on. Okay, that was the idea. That's the model concept that we used. Okay, let me start it first with the free flow. The free flow, we use the runs concept. I will come back to this in a minute. Single phase cars, two component, air and water, non-isothermal, incompressible. We have compressible and, of course, incompressible concepts developed for this. And for the experts, for the numerical part, these are the primary variables. It's very important. We must switch the variables related to the process. That's very important from the numerical part. Okay. Now I come to the first very important aspect related to the free flow system. You can be in the laminar regime and you can be in the turbulent regime, or you can in between. And very important, I will come back to this later on. Normally we are in the turbulent regime, and then you have the viscous sublayer here and the turbulent layer. That means in the viscous sublayer, between the viscous sublayer and the solid, the porous media, you have laminar flow, relative structure, and above you have an optimal mixing related to the turbulent flow. That is the fully turbulent system. Okay, super. And of course, you can have layers for all different processes. That means you get a layer for the momentum, you get a layer for the mass, and you get a layer for the thermal part. That means if you have different kind of components in the system, then it can be that the mass and the energy layer is above or below the momentum. Very important. It's important to know. Okay, that's related to one of my questions too. Okay, so I did all these unclear questions. Okay, let me come. I like equations. Okay, let me come at first to the equations. You are familiar with this. I'm 100% sure. The first one is the mass balance. That means the time dependency and the flux. Then you have the momentum balance. We use the Run's model, different kind of Run's models. I will come back in a minute to this. That means you have the storage term, the inertial term, the viscous term, the eddy viscosity term. We need a model for the eddy viscosity, of course, you know this. Then, of course, we have the pressure and the gravity term. Then, of course, we have a multi-component system. That means, for instance, in this case, X stands for mass fraction. That means kappa is the component, and G in this case is the phase. Okay, we have two components, air and vapor. And then, of course, we have the storage, the advection, diffusion, eddy diffusion, and the source term. And the same for balancing, for the energy balance, but we assume for this case, locally, some local thermal equilibrium, so that we can use one equation for all phases, one energy equation. That means we have the internal energy, the enthalpy, that means the advective term. Then we have the eddy diffusion term, sorry, the conduction, and we have these two ones, and the source and sink. Okay, if you have questions, please interrupt me anytime. Okay, these are the classical models for free flow systems. One statement that was the first big problem, or a mistake that I've done. I thought all these numerical schemes are available for Navier-Stokes equation. It's true, but in general, they decouple the Navier-Stokes equation. It means, for instance, they calculated first the pressure and use then the pressure as a source term for the rest of the transport. But in our case, we have a strongly coupled system between the free and the porous media flow. So we cannot decouple this. Why? The processes are on completely different timescales. We have checked this. So that we need really a monolithic concept. That means we need a discretization scheme that allows us to solve the Navier-Stokes equation in an implicit framework. That's not so easy. That was the first mistake I did. We have now a very nice numerical scheme that works for higher order to get really the turbulent as good as possible approximated, but it's not so easy. Okay, let us discuss it later on. So, and then we used, for the experts, we used an SST model. That means at the wall, we have wall functions, or the K-omega model. The K-omega model is really a model that handles really the transfer from the laminar into the turbulent. That means near the interface from the porous to the free flow. And the K-epsilon model is really a turbulent model that is not valid, suited for processes at the interface between the transfer of the laminar to the turbulent. The SST model is a model that helps us to transfer from the K-omega model at the wall to the K-epsilon model far away. That works very well. Okay, that's a transfer function. If you're interested on the, it's my pleasure. Okay, but this is not the point for the talk itself. Okay, so then we are familiar with the free flow. Okay, now we can solve. We are proud about ourselves. We can solve free flow regimes for the gaseous phase, compressible, incompressible, non-isothermal with different kind of components. Now, that is the porous-medium model. We have started with this long time ago. It's a multi-phase flow model. That means we used in this case classical Darcy. If we have higher velocities, Vorheimer, but the classical approaches. That means we have multi-phase flow, Darcy's law, two fluid phases, gas and liquid, two components, air and water, non-isothermal, equilibrium phase transition, and we assume local equilibrium. That means in one Eulerian control volume, we assume that we have one temperature for the solid and the two liquid, two fluid phases, to try to be as clear as possible. So the equations, I like equations, the balance equations with the storage term, the saturation, and the flux term. Then this is the momentum balance equation, the extended Darcy's law. You have seen it yesterday, relative permeability, viscosity, permeability, pressure gradient, gravity, and the Darcy velocity. Then you have the component mass balance, and we use binary diffusion concept for this to make it as simple as possible. So that you get here the time-dependent term, the convective, advective term, diffusive term, source and sink term. And then, of course, we have the energy balance, again, for local equilibrium. That means internal energy, enthalpy. Then, of course, the storage term to the solid phase and the conduction, the heat conduction. Okay? Are you with me? Oh, it's clear. Okay, super. So, these are the supplementary equations. You need descriptions for relative permeability and so on. You need Dalton's law and Henry's law to get all these kind of things together. Okay. Yeah, to get really a closed system. So now we are proud of ourselves. Then we have thought about the interface condition. How we can describe the tangential and the normal processes at the interface. That is very important. So I would go a little bit more into the details. I will try at first to transfer from the pore to the REV-scale to see what we have done and what kind of mistakes we have done. Okay, that is the pore scale here. That means, for instance, the solid, the gases, and the liquid phase. It's clear there's a non-slip between the solid and the gases, the free flow. Here is a non-slip condition. There isn't any velocity. We have a slip between the gases and the gaseous phase here. There's a slip condition, but the viscosities are the same. And here you have another slip condition between the gaseous phase and the liquid one. Why? You have two different kinds of viscosity, the viscosity of the liquid phase and the viscosity of the gaseous phase. Okay?
Sorry. May I ask a question?
Yeah.
Between the gaseous and the gaseous,
yeah,
is it balanced or asleep?
It's balanced.
Okay.
But you can, if you check the literature, they call it balanced or slip. Why? You have now the gas in one hand in the throat, and then of course you have the flow on the top. You get shear stress there, and if you have shear stress there, then they call this shear stress. And if you have shear stress, then you can transfer this into a slip. Okay. That's the idea.
But based on my understanding, correct me if I'm wrong, a slip is partial transfer.
Yeah,
isn't it?
Yeah. Why I have mentioned this like this one? I need at the end the conditions for this, and that helps me if I use this kind of formulation. That's the reason why I use this. Very good statement. That's easy, but there is one weak point. The first weak point. You use for the free flow the classical balance concept. First and zero and first law of thermodynamics. Okay, with all this kind of concept. That means you have a second derivative of your velocity. But for the porous media for Darcy, you use potential field. Simplification of the crystalline analysis. What does it mean? It means if you build now the balance of the normal forces, then the pressures are not equal at the interface. Why? Here in the free flow, you have the classical pressure of the free flow system of the fluid. In the porous media, you have the potential related Darcy pressure. You have done a lot of work related to this, so that the pressure is not the same. That's the first weak point. We have done dimensionless analysis, and we have assumed, let us try to do that assume that the pressures are the same so that we can use chemical equilibrium and thermal equilibrium for the interface too. But it's wrong. Let me say it like this one. Let me at first state. You see here the difference. That means that is the balance of the normal force. Here. Then we have the tangential one. It's a little bit more tricky. The tangential one, again, now I come back to you. No slip. Here we have shear stress in the system. Let me say it like this. No? And we can use, in this case, the Beaver and Joseph condition. I will come back to that later on, where we build the forces of inertial stress and pressure at the free and the porous media one at the interface. But the Beaver and Joseph condition is the condition in the free flow. So you see it here, that is the Beaver and Joseph condition. That's the velocity of the gaseous phase in the free flow. This is the permeability, that's the resistance here, the average quantity. Then, of course, that's the fitting parameter. We call this Beaver and Joseph condition. That's the viscosity, and that is the tangential vector in the system. And this is equal to the flux in the porous medium. Okay, it's valid very well for single phase flow, but not for multi-phase flow. And of course, it's clear the amount of the different slips is dependent on the saturation if you want to argue. If you have a high liquid saturation, then you have a lot of parts like this one. If you have a low one, then you have a lot of gases related parts. But this, we have done a trick. I will show you this. And this, for instance, is the effective stress. You know this, it's clear. Okay. So then we come to the component related to the assumption that we have used. We assume that the mass fraction at the interface is the same, directly at the interface. Then, of course, we assume that the whole water can be evaporated from the pores directly in the free flow. So then we can build this kind of balance. This is the flux of the convective or advective and the diffusive one in the free flow. And that's the convective diffusive one in the porous media one from the liquid phase and the gaseous phase. Okay, super. And we can do it in the same way for the energy, so that we assume local equilibrium at the interface. And this is not valid if you have a cold stream on the top when you are far away from this, but we assume this. And you see what's going on. In the free flow, we have now the energy flux that I've mentioned before, and in the porous, the energy flux that I've mentioned before. Then you can build the energy transfer under the assumption that the temperature at the interface is the same. Okay, the gradients are not the same, but the temperature itself is. Okay, super. We are so proud about ourselves. Then, of course, we have asked Danny Orr, we have had a project together. Then he told me, Rana, let us do an experiment. Okay, and then you can trust your nice things. So we have set up with Danny together. Klaus visited Danny at the ETH Zurich. He was there for 3 months. They built up. I'm not an experimentalist, try to be fair, I have any clue. This is the sandbox here, that is the free flow. And you know, ETH Zurich has a lot of money. That means they have had different kind of cameras, thermal camera, that's a thermal camera here, to calculate the temperature on the top for the evaporation process. Then they have had measurements of temperature and pressure inside the porous media in the free flow and so on, okay? And that was possible to calculate the whole flux, the evaporating flux in the system, blah, blah, blah. So, great. We are prepared. And of course, there are 2 stages that are very important. Stage 1 and stage 2. Stage 1 means the liquid phase interact with the free flow. That means we have a direct evaporation process from the liquid phase, the vapor into the free flow. And after a while, this box was closed, you get decrease of the water phase, the liquid phase. That means you get the transfer. And if the first layer is empty with liquid, then of course you get only vapor-driven processes in the gaseous phase. That means you get a decrease of the evaporation. That's stage 1, and then it's stage 2. Clear for all of you? Okay, super. So, and then of course we have done measurements. We have different kind of publications. This is one example to show you what we have done. Yeah.
Before I get completely lost here. Okay, so you have this box here.
Yeah. Yeah.
Filled with water.
Yeah.
And then you just let it evaporate without replenishing.
Yeah.
All right. And then you watch how the interfaces are.
Yeah.
Yes.
Yeah. 1 minute, 1 minute. You have a little bit more time?
And of course, it will make a big difference if we put salt in here.
Yeah, yeah,
That's what it is.
now we have any salt in it. But if you like it, I can show you what we have done. Then it makes the situation more clear. Then it takes a little bit longer, my friends. Half an hour, not in minutes. To make it as clear as possible. So I kicked it out. You see what's going on now here. 1 minute, 1 minute, 1 minute. That's the setup of the experiment, Alex. That means this is the free flow. That's the porous media one. Okay. And you see here stage 1, stage 2. That is the setup. And we check it along this green line. Okay. So what does it mean? It means here we will show really the liquid saturation in the porous media, and here the vapor in the free flow. Okay, and here the temperature. And I would like to do it now step by step. Okay? So at first, you see, we get now evaporation. That means if we get this kind of evaporation, at first we have a very high evaporation, then we get the decrease of this evaporation. That's related to the decrease of the saturation in the porous media. You get less and less connected parts from the liquid in the porous to the free flow. You see it here. And then you can see here the vapor in the porous media. It's 100% in the vapor in the porous media, and to get the decrease in the free flow. So, and then you see the temperature. Here, if you have a high evaporation rate, then of course you get this cooling effect. That means, with other words, at the interface, you get the decrease of the temperature. Okay, are you with me? So now we go one step forward. We are now in the transition part. That means we get the decrease of the evaporation rate related to less and less parts that interact between liquid and the gaseous phase. You see what's going on here. You get less and less water in the porous media. The saturation is relatively low. And you get, of course, the decrease in the delta of the temperature related to the decrease of the intensity of evaporation. You are the experts. It's clear. So, and then you see what's going on. This is the process that we have in mind to cover. Yeah. And then we try to measure this now, compare this now with measurements and our calculations. Are with me, all of you? Okay, super. Again, the experiment. And now you see what's going on. And this is the measurement, and we did it not one time, we did it a few times. At the first time, Klaus sent me this and Donny, and I told them that can be wrong. That must be wrong. Then they did it again, and they got the same bullshit. And at the end, we did the bullshit. But that's another story. I will show you later on why. You see, this is the evaporation rate partly that they've measured. You see, that is phase 1. Then they have this tiny drum. That's it. This is cleaning. Huh? Can you change it? Sorry. Tiny full screen. No, sorry. Tiny transition. And what we have done at first, we used the laminar model in the free flow. Okay, laminar model in the free flow. Then you have a relatively thick boundary layer. Okay, it's if you have 3.5 meters per second and you have the gaseous phase, then you are at the transfer between the lamina to the turbulent. You see, we are far away from this. Then we have thought we need turbulent models. We have developed our turbulence model. I've showed you this. And then we use different kind of Blasius concept, the constant, and the turbulent one. But you see, it's nice, but bullshit. Okay. The question is now why. That's a question to you. I will offer you 2 beers if I get a good answer.
Well, your dynamic boundary conditions, even if you assume local equilibrium, don't obey a certain symmetry that I am used to.
You will get 1 beer for this one. I will show you. You're on the right track. But it's not in the game. So what we have done as a stupid engineer, they tried to analyze. No? And Klaus told me, Rainer, let us start to do it step by step. And that's one of my favorite statements, do it step by step. Okay, at first, we have analyzed the capillary pressure saturation. You see how sensitive it is. If you changed a little bit the last part of your capillary pressure saturation measure, then you see you get really a shift, a big shift in the system. It's clear. If you changed it a little bit, then you have this kind of high capillarity related to the tiny change in saturation. And immediately you get then more and more intensive influence of capillarity. That's one reason. Okay, of water. Yeah, nice. Then there's a paper that we published with Danny together. We have analyzed, and that was you have mentioned in your one of your answers. There is a big difference. If you have if you have a fully saturated system, then the interfaces are clear at the interface between the free and the porous medium, darker blue ones. Okay. But if you be in the area where you transfer from the liquid dominated to the mixture, gaseous liquid one, then you get less interfaces and you get this kind of, I call this diffusive mushrooms. That means now you get really this area and behind there isn't any kind of evaporation. Here's only liquid and here's gas and here's the gaseous phase. So that you get the diffusive flux in all directions. And is the board? No, that's the wall. I like to write on walls.
You can also write on the screen.
Yes. Can I do it here?
Yes, and you should.
We have it in Stuttgart too.
Yes, and then you can use these pens to.
Super. You see it here, and that is clear. If you have now here your delta, and you think about your diffusive fluxes in your equations, like diffusion, then it's clear you have the diffusive part here and the diffusive part here. And of course, the interface has a strong influence on this flux. I will come to this. Okay. And of course, if you have this kind of behavior, then this has an influence on the exchange process. We have underestimate and overestimate partly this kind of aspect. I will come back to this in a minute. Then we have started, we cannot solve it. But there are a lot of papers available. If you like it, I can give you, and well cited. The other ones, they haven't had any clue what kind of mistakes to do. That was really great. And then we have decided, let us go back to the REV-scale. At first, we have done DNS analysis, okay? And we have used a staggered system, very simple staggered system. And that is only a part of them, free flow, porous media flow, the same procedure as before. That means, for instance, that we have a box closed, and then we have a lateral flow field on the top, okay? To analyze really the momentum transfer between the free and the porous media. And you see what's going on. On the REV-scale, we get this averaged blue line here. If we use REV-scale fitted alpha, that is the alpha value from Piefer and Joseph, I've mentioned this before, you get this black one here, and REV model constant alpha, it's this one. It means the alpha value describes the inclination between the velocity profile in the free and the porous media. That's not the case. But you see, there are differences in the system for this very simple example. So then we have decided, oh, what's this? This is a new slide. Yeah, sorry. Can we find better coupling conditions? How to choose parameters? That is one of the key questions related to this. So we have decided, let us go to the REV-scale. Okay. If you have questions, please interrupt me. So then we went back to the REV-scale. Say, hey, we cannot solve this kind of thing. We haven't any clue how we can solve it. We need more information about the interface-driven systems that you have mentioned in detail. Okay. So then we have decided we can do DNS calculation, but we can do it on our supercomputer. We have done it on this scale. If we have multi-phase flow with volume and fluids, that's not a solution. And of course, we have capillary-driven systems. We are interested in capillary-driven systems. So that we thought, let us use pore-network. Okay, that was after a long discussion, David Boltzmann and so on, we have decided, let us do simple pore-network. They are not so simple. Sorry, but I was, I was naive again. let's do it for it. And this is, Kilian is an environmental engineer too. He finished his PhD last year. And it's Martin, he's a mathematician, he's a postdoc. We have started to develop a pore-network for this kind. That means the idea was really, you see, allow this, but it takes a while. Give me 10 minutes. So, ready? Now, the idea was really to have a hybrid model at the interface for network and in the surrounding, in a far field, we use REV models. Okay, let me come to this one. You know this very well, what a pore-network model is. We have the pores, then we have the structure, we need segmentation, simplification, then we have the very simple concept. We use a different one to, where is it? Here, your ones, our throat hasn't a mass, only the bodies. You have to do it the other way around. But our wish was really to have really multi-phase flow with non-isothermal, blah, blah. Okay. Then, of course, we were prepared to do this. And the idea was really to get this kind of things into account. I will tell you a little bit more what kind of tricky problems do you get now, challenges, opportunities. Okay. Again, the interface here. You are familiar with the equations that we use Poisson equation. That means, for instance, mass balance, the momentum balance in the free flow that is related to what we have done so far before. Then in the pore network, that means, for instance, the storage term, the flux term, and the source and sink term. Then these are the interfaces. That means, for instance, conservation of molecular flux per species, and we assume in this case chemical equilibrium. To make it as simple as possible. I can in a minute to this non-isothermal. Okay. So then, of course, you can use different kind of local capillary pressure saturation relationships. He's an expert about this. Local relative permeability to get resistance and all these kind of things as good as possible. There are a lot of concepts, but what is the interface? Okay. Again, we have thought how we can solve the interface, but we now in a good position, right? We use now the same concept for the pore network and for the free flow. And that is the advantage. We do not use any kind of potential seal. That's really the advantage. So that means you see now here we have the non-slip. And it was necessary to here at the pore body or the throat to the free flow to calculate the normal and the tangential momentum transfer. Okay, if I'm too late, please interrupt me anytime. So at first, the mass conservation is what's going in, it's equal to what's going out. It's easy. Then you know the pressures are the same. That means, for instance, you use now the same concept for the free and for the porous. So the only what is necessary to do is now to analyze the two forces of inertial and shear. I do it for shear. If you like it, there's a paper for inertial too. It's the same procedure. It's not a big deal. That means at first, let's have a look to the tangential one. Okay. That means, with other words, here the tangential is 0, and here you have a shear stress. Very simple. Okay. The question is really how you can calculate now the shear stress between the pore and the free flow. Why? That's the 1D and that's the 3D approach. How you can bring these things together. Yeah. So what we have done, very simple. We have formulated the equations for both in a general form. That means the shear stress in the free flow and the shear stress in the porous medium. Pressures are the same, and I assume that I would like to show it only for the shear stress. Then we have reformulated this equation, and then you get the slip velocity, this one here at the interface. The problem is here the beta factor. Why? That describes the radius of the system from the 1D into the 3D. Okay, we have done a dimensionless analysis and different kinds of DNS calculations, and it shows that the radius is the beta factor is proportional to the radius. It's relatively easy. We have analyzed this DNS calculation. I will show you this in a minute. So now we have really the interface as good as possible approximate. We can do it for gas-gas, and we can do it for gas-water, and of course for gas, solid. It works very well. So there's a publication related to this with my heat. And then, of course, we analyze this in detail with measurements with colleagues from Utrecht together. You see here, we calculate the L2 norm for this, and it looks not so bad. That means, for instance, we have checked really what's going here at the interface. You see it here, that's a comparison study. If you be in a capillary regime in the porous medium, then it works really very good. You see on one hand, the reference one is the yellow one, it's the DNS calculation. Then, of course, our new concept is the purple one. And with a non-slip, it's the black one, so that we can approximate this kind of things in the normal and the tangential one as good as possible. Okay, wow, we have solved one problem. So now, but that was only one. Okay. We have compared this with microfluidic experiments, with DNS calculation, and with our model, and we got excellently related comparisons. Okay, there's a publication. Now I will show you the effect that I've presented before. That is a 3D case, but I will show you only slides. 3D, you cannot see it. This is the 3D case. Okay, that means that's the porous media, pore-network. That's the free flow one. And in this case, we have a tiny Reynolds number. And you see really related, and this is a no-flow boundary condition, no flow boundary condition. We have the flow in this one, and we inject a little bit components from here, a conservative tracer, to see what's going on. And you see really here the outflow and the inflow based on the structure of the porous media. That means you get really a strong fluctuating process at the interface. And this has an impact on the whole system. That means you get really huge mixing behavior related to the interaction between the free and the porous. Okay? So if you have, now I come back to my boundary layer story. If you have now a higher Reynolds number, then you see directly the boundary layer, and the boundary layer has a strong influence. That means the effective term is not so important any longer. But the diffusive one is very important now. Why? Again, you have then in the free flow, you have a really tiny concentration. In the porous, you have a high concentration. You have a tiny gradient length, so that if you get an increase, a decrease of the thickness of the viscous sublayer, you get an increase of the diffusive flux from the free to the porous and from the porous to the free flow. Very important. Clear? Okay. We did it for turbulence flow. It's a master's student. She will start now with her PhD with us together, with Matt together. And we have done it for turbulent regimes and so on to change. Okay, so now I come to the end of my story.
We would like to have some discussion.
I need only 1 hour. No, 2 minutes. I will do it as fast as possible. So I agree with you 100%. That signal. Now we have done it for non-isothermals. The same procedure as before. You see, the only thing is here that you get really the energy equation into the game. Okay, and of course we have analyzed this for cylindric throats, and we have analyzed this for rectangle throats. And there's a big difference. Clear? Why? In the rectangle throats we have corner flow. We have a couple of different effects. In this one you haven't this. That means, for instance, this one is more realistic than this one. I will show you this. But these are my last slides. Oops, my fell over. We have analyzed the differences. 1 minute. I will show you results. And we can now reproduce what the colleagues from ETH Zurich has measured, what we have discussed so far before, that we can get the mathrooms here, the interactive processes here. That means we are now in the right track. Let me say it like this. You see now what's going on. That is an evaporation process now. That means 100% water saturated. We have a dry gas flux on the top, and we have a wind from the left to the right-hand side. And these are the different throats here. 1, 2, 3, 4, 5, 6, 7, 19. From left to right. At the beginning, we get this kind of flow field. And this flow field controls then the evaporation process. Okay. And you see what's going on. We have now flow field and the evaporation process that controls this one here. Then you have the wall on this side here, so that you get this kind of evaporation effect. It's really tricky to see. That it took us a while to understand this. And you see, if you evaporate more and more, then you get back to the behavior that I've presented before. So now I try to shut my mouth. I have slides about the numerics. We can do it later on. Thank you much for your patience, concentration, and I hope you will have a lot of questions. Thanks a lot.
Oh, thank you so much for the inspiring lecture. I'm sure there are questions here. Who is first?
Yeah, to try it.
Yeah, Dan?
Well, as I now know nothing about the subject, but I might as well start off with this question. So this emerging heterogeneity at the boundary layer, is that something that the people who work on batteries should be worried about?
Yeah. But we have done it for fluid cells. There are 2 brand new papers now available and transported in porous-medium. And that's the reason. 1 minute. I will answer your question in a second. That's my last slide. That's not the answer. That's only a statement. 1 minute. We need a good understanding about the roughness too. And there's surface roughness and topological roughness. So there are different kind of aspects that controls really the mixing behavior between the free and the porous-medium one. That is relevant for what you have mentioned too. Of course, yes.
Great. I see Björn has raised his hand.
Good. Okay.
I give the word to you, Björn.
Thank you very much. And like Signe said, thank you for an inspiring lecture. I have one question not directly related to your talk, but nevertheless, if the surface is the interface between the porous medium and the free flow region seem pretty flat. If that surface is corrugated, would it give more or less the same effect as these mushrooms you showed, or what?
No. Beyond, there are 2 effects. Do you have time to show other slides? No, I will explain it first, and if you like it, I can show you other slides. At first, if you have a wavy structure like this one, then you get eddies related to the wavy structure. And if you have really, if the distance between related to the radius number in the free flow, the distance are relatively small, then you get a controlled eddy between the 2 different peaks. And then, of course, this eddy controls then the evaporation process. That means, for instance, that blocks the system. We have analyzed this.
Okay.
The second one is, on the other one, if there's only one eddy, then of course, if you have in the front of the flow field, you have a tiny viscous sublayer. And related to this tiny viscous sublayer, you have a high velocity there, tiny viscous sublayer. You get a high diffusive part related to this gradient. And behind this, on the other side of this peak, you get the opposite. Why? Related to the decrease, you get a relatively thick sublayer. You get then an advective control system and not the diffusive control system. Last comment to this, and of course the roughness, the surface grain roughness itself has an influence too, that what we have analyzed now in a master thesis with colleagues from Brunswick together. If you have this surface roughness, and depends on the roughness of the surface itself, you get the local mixing, and this local mixing has an influence to the system too. I think, but we are starting now to analyze which one is dominating compared to the other one. Yeah, it was a long answer.
Okay. Well, thank you very much.
Sorry.
Thank you. And Michael?
I have a question regarding the experiment. So you said you can measure the pressure inside and the temperature. Can you somehow also get the boundary layer that you can quantify that?
Michael, I haven't any clue, but we have had a cooperation, or we have a cooperation with Boulder University, and they have a very fancy wind tunnel in the aerospace engineering department. I have slides for this. And what they can do with the, what is this? What kind of technique do they use? I must check it. I'm not the experimentalist, but they can really measure the 3D velocity field. And
PIV?
it's a micro PRV. It's a micro PRV, and they do it in the aerospace engineering. And they do it too. And then they can really analyze not in detail, but as an average quantity, the flow field from the rough surface or from the surface to the first part of the lamina and then to the boundary, turbulent boundary. That helps us a lot to see where we are. Yeah. There's a weak point if you would like to use this kind of models for real applications. The climate experts, they measure all this kind of things above 2 meters. And they are now really under stress to couple the atmospheric model with the water cycle. They are really interested in this. They know that has an impact, a negative impact on the climate. And they ask us now to transfer this. We have now a DFG project where we try now to bridge the gap between these 2 meters to the surface. But we have started with this. Sorry. It's clear, Michael?
Yeah. Question from me.
Yeah.
I mean, the primary validation is of a model is, of course, with the experiments.
Yeah.
But since you are on the theoretical side, I dare to ask whether you did consider also using the balance equation, which nobody is using, namely the entropy balance.
We have done, you know, we do it to see really is the entropy really entropy condition fulfilled. We have started with this.
Yeah.
We have done it only for the porous-medium one, but not for the interface.
Because you could sometimes distinguish between models in that are consistent or not.
Consistent, yeah.
So you get this information about a consistent set of approximations.
But Signe, we are not consistent in the REV concept. Why? Very simple. The bullshit, that's a stupid word, but the weak point is that we use different kind of model concepts. We use the fully one in the free and the potential theory in the porous-medium one. And then of course you can calculate the chemical potential, but if you have differences in the pressure, if the pressures are not the same, then of course immediately the concentration are not the same and the temperature are not the same, but it's not dependent from the physics, that's dependent from the model.
Exactly.
And this is
but
you know what I mean.
That is what I was then possibly hoping to achieve, that you could sort out the goodness of the various models.
What we have done, but as a stupid engineer, what we have done, we have calculated the potentials for the different things, and then we have done a dimensionless analysis to see how far we are from the real system, to get a feeling. And then we have decided it's too complicated with us, it's okay. Finally fair. Now it's really, there are so many open questions. Yeah.
Well, I think we close this.
Alex,
Oh, sorry.
Alex, sorry. Yeah. You know,
we have these really 2 liquids and interfaces. Yes. I was just wondering, you know, if we were to use that model in this setting, of course, we would need to have really pass from the inside with no interfaces otherwise, because of these velocities. I agree. So, yeah.
We can iterate about this. We can compare this. I'm 100% sure that there must be differences related to the moving interface. But can you calculate how corner flow process is?
We have a version of that.
It's important, you know. If you're in the stage from the transfer from the stage 1 to stage 2, you have only tiny parts in the corners of your porous-medium, related to capillary forces. Okay. And this controls then the main part of the evaporation. That's the reason why they use corner flow as one of the aspects in the system too. Can I give him an additional answer? Is it allowed? very small. If you like it, I can show you. These are not published. If you have solved them, then you see what's going on. The salt is only in the liquid phase. So if you have now a strong evaporation, then immediately you get a high concentration of salt in the rest of the liquid phase. And then you get immediately precipitation. If you get this kind of precipitation, then you get directly a change of the cross section. And you get then a capillary dominated system. That means you get a decrease, a shrinking of the cross section. If you get this shrinking, Laplace equation, you get an increase of the capillary forces. Then you get directly an upconing and you get an increase of evaporation. It's, yeah, okay.
We have no, Alex.
Like when it's one sentence.
Yeah.
It's developing now. Model where column flow is central and there's experiments in Moscow, and it sounds to me like that model could be used.
Very good. Yeah.
Yeah.
When? Right? Tomorrow.
One idea is this different nanocrystal that we have done. Is over here and the pre-flow regime, they actually
So it is.
boundaries on evaporation takes place.
And the good news is we have nothing by definition. Sorry, they have done the work here. All my colleagues here at the team. Try to be clear. We have done experiments with bitter together, so that we can analyze really the evaporation process that takes care between the free and the porous-medium. If you like it, we can share it with you. That's not a problem. But that's yeah. I think I try to get them out. So
I'm not sure you, because we have more options. So stay tuned. At 12 o'clock sharp arrives a pizza, and we will just mingle and talk and ask any question. And then you have to protect yourself.